And it's good to see everybody. And we are getting very near the end here. There are only 9 days left. 9 days left in the quint. And so we're getting near the end here. And hopefully if you've been doing your due diligence, which is attending live sessions and watching all of the videos for each of these sections and going through module 4 and clicking on those little hints and tips and whatnot, and been emailing me for assistance, students have been doing well, and I look forward to continuing to work with you and hopefully help you reach your goals for this class. Let's see, we've got a question here from Romilly. What can I do for you?
I don't know if it's just me, but your mic is sounding really robotic right now.
Robotic. Let me just double check and make sure it's plugged in. Sometimes when it uses the computer mic, it's doesn't work very well. So
Yeah, it sounds good now.
We're good now?
Yep.
Now everything sounds normal?
Yeah.
Okay, excellent. Where was I? Oh, all the exams have been marked, and I tried to provide you some feedback in the practical sections. The next exam will be a similar format, except instead of the first half of the exam or the sort of theory and knowledge-based section of the exam, instead of that being all multiple choice, there are several questions in that section now where you have to provide me with a little bit of code, just little code snippets inside your answers. So for instance, I might ask you to, I might give you a string and say, you know, X equals the word hello. Write one line of code that will slice that string so that it prints HEL or something of that nature, or ask you to build a specific function with specific arguments and specific parameters, or that you need to return a specific calculation or piece of data. So you need to be very, very familiar with the things from the first exam, because the second exam basically takes those things and then builds upon them. So you're going to need to know both. It's not like you just need to know 4.1 to 4.4 for the first exam, and you just need to know 4.5 to 4.8 for the second exam. For the second exam, you really need to know everything. So we're just kind of adding to it. So if you found that you were having trouble with, particularly with string slicing, fruitful functions, and that is sending arguments, turning them to parameters, returning data. If you were struggling with if statements and conditionals, or with comparing pieces of data using greater than, less than, greater than equal to, less than equal to, equals, not equals, those are things that you're really going to want to fix between now and Wednesday, where the next exam opens up. The next exam is also over several days, so I'm going to open it on Wednesday at midnight. So basically all day Wednesday it'll be open, and then I ask for everything to be submitted by the 27th. So it's a shorter period of time. We're getting near the end of the semester, and also at this point your skills should be strong enough that this exam doesn't take probably as long as the first one. When I do these exams inside a classroom, they're still open book, but the students only have 2 hours to complete them. So essentially you're getting 1, 2, 3, 4, 5 full days to complete a 2-hour exam, which should be plenty of time. So as I did with the first exam, I'm going to strongly recommend that you attend all the review sessions, continue attending the live sessions, continue emailing me questions, and make sure that you're completing your assignments, because the skills that you need to demonstrate on those assignments show up on the exam. So that's why we do them, right? And don't leave it to the last minute. I had some students who emailed me at the last minute and said, yeah, I don't know how to do certain things, and then I said I will do my best to help you out, whatever concept you're struggling with or whatever assignment you're struggling with, but the exams are not going to be postponed. The exams are not going to be submitted late. Everything else in the class you can redo. You can if you choose to, you can submit it late and I'll still grade it or whatnot, but the exams are non-negotiable, as is the final project. And some students have already asked, I'm doing really well, I'm getting great marks, can I just kind of carry on and pretty much finish up the course early? I said, absolutely, go for it. If you're doing well and you understand what you're supposed to understand, and you're turning in all the assignments, and the marks you're getting on the assignments and the feedback you're getting matches up with what your goals are for the course, by all means, if you want to finish it early, go ahead and finish it early. And if you feel like you're struggling, continue to email me those questions, continue to come to these live sessions, and make sure you're accessing all of the learning materials that are available on the class website. One other thing that I'd like to mention from the exam is that there were several students who lost marks in the practical section just because they didn't read the assignment. Okay, take your time. You've got a lot of time to do these exams. It's in your best interests to read things over carefully because it very clearly states in bold, I think a couple of times, you need to get full marks. You need to have inline comments for all of your programs. You need to use fruitful functions for all your programs. And also I gave you example input and output data, and it's it's your job to use the skills that you're supposed to use and to read the requirements very carefully so that your program, when you submit it, matches mine with regard to the input that you are asking me for and the structures that you're supposed to use when completing the question, and also the output that you get matches up with the format and data types that mine do. So I think there were some people that lost some marks that really didn't need to if they had just read things over carefully. So with that being said, we're going to move on to just a quick review of some of the information in 4.7, I believe. Let's check the calendar here. 4.7, and I don't think I'll touch on 4.8 today. I think I might leave that for next week's Wednesday, which is basically just the start of the second Python unit exam. And today I just want to deal with lists, and I want to deal with dictionaries because they're both very important parts of our Python, of the Python programming language, and the structures are very important with regard to how you store and access data. I mean, computers are very good at doing math, and they're also very good for storing information and allowing you to quickly access information. And we've gone through several examples of how you can make yourself a lot more efficient using technology and using programming if you are structuring your data the right way. But what we haven't really done a whole lot of, haven't put a whole lot of focus on yet, is storing multiple pieces of data. We've got lots of experience creating variables of a certain data type and storing single pieces of data. For instance, storing an integer, or storing 3 integers in 3 different variables, or creating variables and storing certain strings in them and whatnot. We've done a lot of work with that, so we do know how to store and retrieve data, but we haven't really done a whole lot on storing multiple pieces of data, because making a program that does a simple calculation and does it one time for one piece of data is of no value. You're probably better off just doing it on paper and checking it with a calculator. But when we get to larger data sets where maybe you've got 1 million pieces of information and you need to search through those 1 million pieces of information to find the 5 important ones, that's something that would take you a lifetime to do if you were trying to do it by hand, which is why we have to structure things appropriately. We have to be able to store large pieces of data, or large sets of data. We have to be able to access those pieces of data and manipulate them as we see fit to solve our problems. In reality, in the real world, particularly if you're dealing with data and information that's going to be used on the web, you're going to be using databases to store a lot of information, but that's sort of a level up from what we're going to be doing in Computer Science 20. That might be something that would be more appropriate for a Computer Science 30 class, or even if you've got a particularly ambitious information processing 10, 20, 30 teacher, using Microsoft databases to just understand what databases are and how you can use them to store and categorize information is very, very important for programmers. Anybody who works in a web-based programming environment is going to be using databases to store the majority of their information. They're not going to be storing their information in the same file that they're accessing their information. But again, we're learning, sort of from the ground up, so we're taking it from a focus more on building the structures properly and getting repetition in building the structures properly, as opposed to taking, a real world 1 million piece complex data set and trying these same things on that, because it would just be too complex for an entry level class. So just be aware that these techniques that we're using to store more pieces of data, access more pieces of data, and work with more pieces of data will work fine in our context. It'll work fine for the vast majority of smaller programming projects you're doing. But that if you're willing to take it to the next level with regard to going to maybe post-secondary school and learning more about programming at like a SAS Polytech or a university or some sort of technical training program, you are definitely going to be getting into storing data away from your main program in a database. And then the goal of your program will be to access the database, get the information you want, sort it how you want, categorize it how you want, do the math that you want, and then restore it at a different place in the database. So that you've really got one file talking to a database, which is basically just a series of information organized in a specific way. So your program communicates with the database sends back information, you process it, do whatever you need to do with it, display it, use it on the web, whatever, store it back in the database, and just keep doing that either manually or more likely in an automated process, because databases are just so much better at storing and categorizing and protecting larger data sets. So that's the way it works in industry. That's the way it works with all web-based programs. Google does the same thing. And all the big ones will work with their data that way. But that separation between our programs and our files and larger data sets in a different location is more of a computer science 30 or beyond into university, technical school, etc. kind of level. All right. So that being said, storing of information and large pieces of information is extremely important in computer science, and in Python. We've got some structures that we can use that make it quite easy to store and retrieve and work with and replace data within a big system, think of it just as a storage locker. It's a storage locker that you can store whatever you want, and whenever you need something, you can go open the storage locker and take it out again. And maybe you take out a piece of paper and you write something on the piece of paper and then you put it back in the storage locker. So we're going to be thinking of these large data sets being stored somewhere else. And the somewhere else is typically a list in Python. It's just it's a digital storage locker that you can store any type of information. It doesn't have to be an integer, a string, a float, a Boolean. It can be pretty much anything you want. Any piece of data or data type that you can conceive of, you can store all that information in one place and access it. So that's what makes them really handy. At this point, I think I'm going to shift over to showing you some of this in PyScripter so you get an idea as to what lists are and how we can populate them and how we can do things with lists that help us solve problems and just get some practice with the basic structures that we're going to use to store data and manipulating the data that we take from it. So I'm going to share my screen. Okay, can somebody confirm for me or disconfirm that you can see my PyScripter?
Yeah, I can see it.
Perfect. Okay, so when we're dealing with lists in Python, a list is usually noted with, they're in blue right now, it's kind of hard to see, but with the square brackets. And we've seen square brackets before when we were dealing with, maybe if I just back, there you go. See, that's a square bracket to open it up. We've seen those square brackets before when we've done string splicing, or string slicing, sorry, where we have, taken a string, let's say, x equals hello, and then we've grabbed a piece of that string or printed a piece of that string using the index numbers for each character, whereas H starts at 0, E is 1, L is 2, the second L is 3, and the last letter, the O, is 4. And I'm not going to rehash all that ground because we've gone over it in videos, we've gone over it in live sessions before, but this is a quick review. If I wanted to print the last letter of hello, I can access it by saying, okay, X contains the string hello, and then I could use the square brackets, and either I could use 4 as the number, because the O is in the 4th position, to print out the O. Just run it here. So you see it prints out the O down there in my output window. Or remember, if we don't want to start counting from the front at 0, we can start counting at the back at -1. So if I want the O, I can also print X square brackets -1, and the negative tells it just start at the end of the string instead of the beginning, and then print backwards. So I only asked for one character, I asked for the last character, so again, I got O. So we can refer to O as either the 4th element or the 4th index, or the -1 index of it. And the same thing, it just works from there, right? Like if I try to print x1, it's going to print the E, because the E is in the 1 position. And alternatively, that would be the -1, -2, -3, -4 should also print E. So you could refer to the E, at least the position of the E, as either in the 1 position or it's in the -4 position. And if you print that out, it'll print out the exact same thing. And we also discussed how we can use spaces, colons, and numbers in order to grab pieces of that code. So for instance, if I want to print from the beginning of the string to maybe the first L, that the first L is in the 0, 1, 2 spot. So I'm going to put the one higher than that, right? Because it always stops one before the number you have. So if I print X square bracket, and then I just leave a blank, but I have the colon, it's the blank tells me start at the beginning of the word. The 3 tells me stop actually tells me stop before you print the third index character. So it's going to go from 0, 1, and 2, which should print out HEL. There you go. And remember, if you've got, maybe you've got a starting point, but you've got a colon and then you've got nothing after the colon, it's going to start at character number 1, which is the E, and it's going to print to the end of the word, which is the last O. So it's going to print LO without the H. And then also, just one last review piece here is if we put another colon in, this will tell us, or this will allow us to step through. So for instance, if we start at the 1 character and we want to end at, let's say we want to end at the 4th, I'm going to add a few more characters in here just to make it a little easier. So we'll start at the 1 character, which is the first E, and we'll end at the, let's say, the 10th character, or the character in the 10 spot. 1, 2, 3, 4, 5. Sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I print just from 1 colon 10, it's going to start at the E and it's going to end up at the A right here is in the 9 position, because remember it stops 1 before the number. So the S would be in the 10 position, but it doesn't print the 10. It stops at the 9. To be more accurate, it stops at the 10, but it stops before it prints the letter. So if I just print from 1 to 10, I get the ELLOASDFA. And if I put another colon after that and I put a number, it's going to jump each time. So if I want to print every second letter between those two, I could use a +2, and then it's going to print every second letter starting at the E. So it starts at the E, skips over one of the L's, hits the second L, skips over the O, prints the A, skips over the S, prints the D, skips over the F, and prints the A, and then it's done. If I want to skip by 3 letters each time or 3 positions each time, I can do the same thing. It just prints every 3rd character. And then another thing, one of these was important on one of the assignments. I need you to print something in reverse letter by letter. There's a really easy way to do it with this string skipping or stepping, because you can go backwards as well, right? So you could go backwards by using a negative. Except if you're using a negative, you want to start high and go low, right? Because it's going to be going backwards. So you want, instead of starting at 1 or 0, you want to start at 10 and then go all the way to 1, stepping backwards 1 at a time. So now you'll notice that what it prints, SAFDS, okay, that's starting at this S and then going back to the A and then back to the F and then back to the D, S, A, and then to the hello backwards. So you can use that to access things from the back of the list to the front of the list, or the back of the string to the front of the string, or if you have a positive number from the front of the string to the back of the string. I should probably put an actual word in here. So let's just call it computer science 20. Makes it a little easier to see where we are. So if I were to run the same operation on computer science 20, you see that it's got computer, or at least from M in computer backwards, and then it's got CS backwards as well. So it starts, where did it start? At the M in computer? Starts at CS. There, sorry, it starts there. So that's the SC in science. It starts at the little c, then it does the capital S, then it does the space, then it prints the RET, moving backwards in computer all the way up to the M. And that's where it stops, because that's where I told it to stop. I told it to stop at the 1 character. The 1 character would be the O, but remember, it stops. It doesn't print the O. It stops right when it hits the O, or it stops right when it hits that 1 element. So using the same logic, if I skip backwards by 2 letters every time, it's going to print fewer letters just because it's skipping over some. So again, it's still starting at the small c in computer science, but then it's going to skip over the S, print the space. And then it's going to skip over the R, print the E. It's going to skip over the T and print the U, and then it's going to skip over the P and print the M. You want to skip backwards by 3 steps. And these are things that you should be playing around with. And in fact, as I mentioned last session, you really should have PyScript or Orthony or whatever open as we're doing these sessions, try out some of these things, or if you want to go back after the fact and try them out, that's great. But it's one thing to see something modeled for you, and it's completely another thing for you to, to try it yourself or to create little examples to test yourself on it. And that's the best way for you to gain experience with these structures. So we've seen the square brackets before, but we've seen them and used them with regard to strings. Now, lists in a lot of ways work similar to strings in the way that we store data. So a list is very simply created just by creating an empty list. So maybe I'll call it list 1, and if I just put 2 empty brackets back to back, again, it's kind of hard to see, but because it's in blue, but if you put 2 brackets back to back with nothing in it, it creates an empty list. So if I were to print this list, so if I go print list 1, it is going to work. It's going to print it, but there's nothing in my list. So you see, it just prints the empty brackets. There's nothing in there. Every time you try to print a list, like an entire list, it also prints the square brackets. So your output will include the square brackets if you print an entire list in the way that I did it above. If you print certain things in a list, it won't necessarily include those square brackets. So you'll play around with that in the assignments and as we go forward, and you'll see how that works. So I've got an empty list right now. It's called list 1. There's nothing in it. I can add things to my list manually, or I can add things to my list in a loop. So I'm just going to add some things to this list manually. Instead of starting an open list, though, maybe I'm gonna start my list with some data in there, and I'm going to just use integers right now. But it's important to know that you can store multiple pieces of data. In fact, that's probably something that's really easy to demonstrate. Maybe the first thing I'm going to put in my list is an integer 4. Just randomly pick 4, and then 5.5, and then maybe 3.14, and then maybe the word hello, and then maybe I'll store some Boolean. I'll store the word true. You can store any data type in here. I'll put another integer, another integer 4, and I'll put another decimal in there, and maybe I'll put one more word. So I'll put hi in there as well. So you notice I've got all the major data types that we have been working with so far. The integers, strings, Boolean, and floats are all in this one dictionary, and that's fine. And that's what makes it such a handy sort of storage locker, is that you can store any type of information in here and access it. So you don't have to have one list just for strings and another list just for floats and another list just for integers. You could store all sorts of things in lists. Now, just a second here, I see that there's a comment. Nope, the comment was just yes. Okay, so we're good. So our list up here is, I can print out the entire list by doing print and then just the name of the variable. Remember, this is just a variable, except instead of it being x equals 5 or word equals hi, it's this list equals those pieces of data. So I can print them out just like I print out other data. So by printing list 1, now you're going to see it prints out the entire list, just like you see it up here, and it's got the brackets on. When you tell it to print a list, it prints the whole thing. Okay, now we can print certain things inside the list, and we're going to go through that as well, but that's what happens when you print an entire list. So you see there was no problem there printing out any of the multiple data types. That all worked really well. So let's start looking at how can we add things to lists, how can we remove things from lists, and how can we use some automated structures, some looping, to make adding and making and building lists and editing lists a lot easier on ourselves. All right, so there's some dot notation methods that are assigned to a list or that work with a list, and they're just built in. Remember those built-in functions that we've been using and talking about? Those are called methods, and they're part of a class, which is something you're going to learn more about in Computer Science 30. It's a bit too much for the Computer Science 20. What we need to know for this particular course and for this particular utilization of Python is that there are certain functions that are built in, and we've been using them for the entire course. In Reborg, .move was built in. You didn't have to know how to do it. You didn't have to build a function for it. It was built right in. Turn left was built right in. With strings in Python, we've gone through lots of methods that were built in already, and methods slash functions that were built in already. We've used the length function. We've used .lower to do a lowercase. We've used .upper to make things uppercase. I've demonstrated .strip to get rid of spaces at the end and the beginning of strings. We've used these dot notations before, and just like they exist in strings, there's lots of them that are built in for lists specifically. So let's look at a couple of those and how we can use them effectively. So the first one is append. So what append does, append means to add to. So appending just means add something to the end of the list. So you got a shopping list and you're making it, and every time you add a new item, you're adding it to the end of the list. So that's what append is used for. Let's say we wanted to add a word and we wanted to add maybe one more integer into this list. We can use append. So what we do is we just type in the, we're not printing this, we're just doing it. So we're going to type in list one because we need to identify where is this list and what's it called. And then you'll notice that my little code completion thing, which you'll have if you're in PyScript or Thonny or any big development environment, it just gives you that little code completion thing. It's going to say, well, there's only one list that sort of fits that. It's list one. So if I hit tab and then I hit dot, then it shows me all of the possible methods that I can use, or the built-in functions I can use with list one. And there's a ton of them, and we're not going to do all of these, but we're going to do some of these. And because alphabetically speaking, append just happens to be the first one at the top of the list, that's the one that we're going to use. So you can either type out append, or you can just hit tab in PyScript and it fills it in for you. It's called auto code completion or auto completion. So dot opens up the list of these are the built-in functions that we can use. And then if I put the bracket in, this is me telling the append function, what do you want to add to the end of the list? So whatever you put inside those brackets is what's going to be added to the list. It's kind of like a print statement. Whatever you have inside the round brackets is what's going to be printed. In this case, whatever you have inside the round brackets is going to be added to the very end of the list. So I'm just going to add a word right now, and I'm just going to call it end, and that's going to add it to the end of the list. And maybe before I add end, I'll add one more number. I'll add the number 99, Wayne Gretzky. So that's an integer. And then right after it, I will do another append statement, and I'll add end just to kind of indicate that this is the end of the list. But really, it's a string, right? It's the word end. So if I do that, and then I print out my list again, not licensed list one. So if I append those two pieces of data and I print my list again, we would expect that I get something that looks like this, but has the new information in it as well. So when I run the program, it prints out the original list because I never got rid of this line, but it also prints out the new list, which, as you can see, includes the items that I appended in the order I appended them. Because I appended 99 first, it got added to the end of the list first, and because I appended the word end second, it's the one that goes at the very end. So you could do that forever. You could append items and keep adding to your list forever. You could also add other lists to lists. So if you had two different lists, let's say you made a shopping list and your friend made a shopping list, and you didn't want to have to write them all out again or add all of the items one to the other, you can use the plus sign to just add them both together. And it really, one just gets added to the other. So if I have, let's say I wanted to add more to this list, but it was a list that my friend had. So I'm just going to make another list here. So this is list 2. And I'm just putting some random stuff in here. So I'm gonna put in, a sentence. This is list 2. Okay, so that's a string, that's a sentence. I'm gonna put in the number 6. I'll put in the number 88.8. I'll put in false, which is Boolean. Okay, I could put whatever I want. So I've got a second list now. And what I can do is I can actually add those two lists together and restore them as another list. Now, here's something that you need to know. If we just print out, okay, so I'll get rid of the original print statement. If we just print out something like print list 1 plus list 2, this is what happens. It does add them together, and it prints it out with the first list first and the second list second, and it adds them all into one big list. Okay. But I didn't actually resave that information. So there's a couple different ways that I could update it instead of just printing it out, okay? Because right now, I printed out both those lists as one big list, but I didn't actually change either of them. So if I were to print out list 1 again after that, it wouldn't have all of the new information. It would just have the original information. I'll demonstrate that. So if I print out both lists together using the plus sign, concatenating them, just like we would with strings, right? You can concatenate or join strings using a plus sign. We can do that with lists as well. So if I'm printing list 1 plus list 2, it did give me the output I thought I would get, but watch what happens when I print list 1 again after that. So this would be the list where it added the two of them together with the plus sign, but you notice when I printed the first list again after that, list 1 is still what I had in there originally, well, originally plus these two things that I appended. So it didn't actually change the list. It just printed it, back to back with the other one and into one big list. So if you want to actually change a list and make sure that you're adding the full second list and changing it for good, you would need to do something more than just printing it. Now we know that if we have a variable, let's say a variable x equals 5, we know that we can change that and somehow resave it as x. So in the future, when I print x, if I change it and then print x again, x is forever changed. So the way you do that is you typically just reassign the variable. So you take the original x variable and then you make it, then you use it on the other side of the equal sign as well. So for instance, we could say that this is the string version of x, right? So if x used to be an integer 5, I can now say, x, I want you to take yourself, turn yourself into a string, and then restore yourself back in x. So in this case, when we did this for the data types, for the variables example, and you could do something very similar with lists. So instead of changing this to a string, I'm just going to add 1 to it. So I'm going to say, instead of x being 5, I'm going to say x is equal to x plus 1, and then maybe minus 10. Okay? So clearly, that's going to be different than 5. But it's still going to be stored in x. So let's look at that in step-by-step. Remember, step-by-step is the best way for you to debug your programs. And if I give you a structure and it works, but you don't really understand why it's working, it's really, really handy for you to step through line by line, watching your variables and seeing how things change as you execute each line of the program. It's like the little step function in Reborg. You could do it one step at a time to see, this is my command, or this is my little piece of code, and this is what Reborg does. This is the next piece of code. This is what Reborg does. And it's just the best way to troubleshoot. In fact, it's the only way to do it with really complex programs. I'm going to bring up my variables window again, as we always do, so that we can keep an eye on our variables. All right, so let's just run this step by step, and I'm going to comment out the list stuff for now, just so we don't have a whole bunch of stuff printing. So what's going to happen when I step into my code? And remember, it's different depending on which program you use. I'm using PyScripter, so step-by-step is F7 for me. In Thonny, I honestly can't remember what it is. I haven't used Thonny in a while, but it might be F9. So this is not something that's common to every single development environment that you type code into. It's specific to each one. So make sure that you go up to the debug section and find out what step into, step over, and step out of are, because those are things that you tend to have to use when you are debugging your code. So anyway, for PyScripter, it's F7. So I'm just going to step through this line by line. It skipped over all the stuff that was comments. Okay, that's normal. And then the first line of code is that it actually runs is line 10, which is x equals 5. So you'll notice now in my variable window, which I can't make bigger, sorry, that x is an integer, it equals 5, just like we would expect it to. The next line prints x, so you can see it printed down here in my interpreter window. And then what happens on the next line is we take the original x, we add 1 to it, making it 6, and then we subtract 10 from it, making it ultimately -4. And then what it's going to do after it does that math is it's going to store it back in x. So when I run that line, now you'll notice x is still an integer, but now instead of 5, it's -4. I've changed it forever. So I can never go back to this original x where it equaled 5. I changed it and I wrote over it. It's like if you're doing an essay, and I'm sure this has happened to people, if you're writing an essay and saving it in Google Docs or Microsoft Word or something like that, and let's say you call your file save, or essay, sorry, let's call it essay. So you save as essay.docx or whatever the file extension is. If you go to that file and open it up and then delete everything and save it again, okay, it saves over the old version, right? And I'm sure people have lost information and lost projects and lost essays that way, just because you accidentally deleted something and then you saved it. You saved over the old copy. Well, the same thing's happening in Python. We changed the value. We used it, but we changed it, and then we stored it back. It basically saved it over the old one. And when we say saved it over the old one, in this case, we're just referring to a little memory slot in the computer, a digital memory slot in the computer, a little bucket that used to contain the integer 5. We took the 5 out of that bucket, and we put a -4 into the bucket. Now, forevermore, unless we change something else, that's going to be a -4 in that bucket. So when I print X out now, instead of printing 5, it's going to print -4 because we changed it. The point of all this was, because we know this already, we've used this skill. The point of this is that once we create a list, if we want to write over that list with something different, we need to use the same sort of process. I'm just going to uncomment my code here so that it works again. Uncomment my source code. So we've still got list 1, we've still got list 2, we still added a few things to list 1. Now what we're going to do is we're going to combine list 1 and list 2, and then we're going to save it as list 1 again. So we're going to take the original list 1, and we're going to say, you're going to be overwritten with a combination of yourself, list 1 again, but we're going to add to you list 2. Okay, so what I'm going to do up here before I do that is I'm going to print out list 1. So let's print list 1. And then we're going to change it so that we write over or basically use list 1 and then add list 2 to it, and then we'll save it over list 1. So now when I print list 1 again, it has been changed forever. Okay, so I don't want to go through step by step on this one because I'd have to do every piece of data and it'll take too long. Okay, but what you need to know is it's first going to print list 1, okay, after it has appended these things. Then it's going to print a different looking list, the new list 1, which is going to have list 1, the things we appended, and also list 2, all of it combined into one list. So when I run this, you'll see the first time it printed, it just printed the original list 1 because I told it to right here. And then the second time I print it, it's a new list that has everything from list 1, the appended item, as well as list 2. And anytime that I access list 1 after this, I print it, I could subtract from it, I could add to it, I could append one more thing. So let's take our new list 1 and let's append one more thing to the end. Okay, so let's go list 1. Okay, dot append. And then we're going to add, maybe let's add one more word that says this is truly the end. One more sentence. And then I'll print it again. So we've got our, what do we got here? We've got our original list is the first thing we printed. We've got the new list 1, which contained list 2 the second time. And then we appended something to that, and then we get that full list 1, including the new addition to list 1, which is the string that says, this is truly the end. So by using either the plus sign for concatenation or for using, if we're using append to manually add things, you know how you can add things to an existing list. So that's an important skill right there. All right, so let's move on a little bit here. You know how to do that. And I'll just keep those append in there for that. Okay, now I've got .del in here, but it's actually not a dot notation. So in that case, it's actually not a dot notation. The question was, how did they code before there was code? And it's a great question. And it's important to understand that. And we're going to do a little bit more on computer history. I put it as the last item because I really like jumping right into sort of planning and programming and coding. But we're going to do some computer history for Unit 5. And what we will see in Unit 5 or Module 5, sorry, is that computers have been around for a lot longer than most people think. A mechanical computer predates an electric computer. So we right now we're doing, everything is digital, everything is electronic signals and transistors and so on and so forth. But before that, before they had electricity, there were actually computers that used levers and gears and punch cards to do specific things like weaving patterns into rugs. Instead of having a person having to do it sort of string by string or thread by thread, they would program machines. In fact, Jacquard Loom is what one of them was, where they would put in punch cards. They'd have these big rolls of punch cards, which basically just had holes in them in specific places. And this roll of paper, really tough paper, but this roll of paper with this pattern of holes in it would be used by a loom to correctly organize threads in order to make carpets or rugs that had specific patterns on them, which took a lot less time than a human being doing it manually. So, even back in the, in the 1800s, they were trying to find ways to produce materials or to solve problems using these machines, because they were recognizing that if you did it mechanically, A, it would work faster, B, machines would make fewer mistakes, okay, and C, they could be continually updated. And that was essentially the start of people being replaced, or human workers being replaced by machines, which, as you well know, is something that's a real concern today. On one side, you get so much more productivity, and it costs so much less, and it's so much less prone to error than human beings are, which are all great things. But on the other side, it could put people out of work, which obviously impacts human beings and families and civilizations and cultures. So they've been using computers for a long time. Now, that's probably too far back from what Taylor's asking. Taylor's asking, before we were coding Python, how did you tell a machine what to do? Well, essentially, computers are all based on the idea of binary logic. And binary just means there's two states. It's kind of like an if statement, right? It's either true or false. It's on or off. It's up or down. It's never both at the same time, or it's always one or the other. So we typically think of zeros and ones when we're dealing with computers, where one was the sort of a computer or digital equivalent of flipping a light switch on, and zero was a light switch off. So you could, it could be one or the other, but it couldn't be 0.5. It was either on or it was off. And in the beginning, we were actually dealing with like real physical switches, like little pieces of metal that you could, put up or put down, whether it was on or was off. And if you combine enough of those switches together, you can get it to represent characters and represent ideas. So for instance, let's say I have 8 switches and all of those switches are turned off. Well, then if all of those switches are turned off, maybe that represents the number 0. If the first 7 of those are turned off and the last one is turned on, maybe that represents the digit 1. Okay? If the first 6 are turned off and the second last digit is turned on, maybe that represents the number 2. So you see how you can use these sort of on-off switches to represent different ideas. And if you string enough of those bits and bytes together, 8 of those, zeros being a byte. If you string enough of those ideas together, eventually you can make larger numbers and you can use them to make decisions, and it sort of starts from there and scales up. Originally, there were people had to use these switches to build some sort of system to make it easier to program things, and it's generally called machine language. And it's it's not particularly complex, but it's really, really long, because you had to have a whole bunch of on-off switches just to represent the smallest ideas or the smallest pieces of data. So they created this machine language to say, here's 10 lines or 10 pages of code that just does one simple little thing on a screen. And that's a really inefficient way for modern day programmers to program. So what they did is they built other programs that made some of the machine language easier to use. So instead of me having to type almost like a function, where the machine language was really, really long, so I didn't really want to have to copy and paste that every time I wanted to do something. So they created different languages, different programming languages that used fewer words and but specific words, syntax. Remember, we can't make spelling errors and stuff like that, to reference larger chunks of this code, so that you could make better programs in the new language without having it, be this long, your code being this long. And then there were people that built on top of those languages. So, every time you get sort of a new language, the goal is to make it easier for you to access all of these really low-level things. When I say low-level, I mean the things that are closest to the computer that tell, the processor what it needs to do, and that, what's the input and what's the output. All of that stuff on an actual physical machine needs to run with that really, really complex, long machine language. So as you built on top of it, the idea is to make it easier and to get you further away from all that really tedious, crappy code. So when you were dealing with computer languages, we're like several steps up the ladder. And the goal of those steps is to make it easier for you to access the ladder below without actually having to go down to that step and build all those things and then go down to the very bottom. You want to try to be able to solve the problems at the high level because it's easier and it takes less time and less code than having to go all the way down to the bottom step and think through all those little zeros and ones to organize what you want. So that's the concept of abstraction, and you'll learn a little bit more about that in computer history. But the idea is you don't have to know what order the zeros and ones go into in order to pass this class. Okay? You need to know how to use Python, which tells the next level down what to do, which then tells the next level down all the way down to the zeros and ones. And that is what that's referring to, is you are abstracted from the little details. Because the little details aren't important to you anymore, because nobody solves problems with computers, at least 99.9% of the world, doesn't solve those problems with computers by knowing machine language. They solve the problems with computers and programming language because they know something that eventually can talk to the machine language and tell it what it needs to represent. So the further you are away from those tiny little details, the more you can get done. So Python is one of those ways that we take ourselves as far away from those little details as we can to allow us to do more, to do it better, to do it more efficiently. Otherwise, you'd never get anything done in a day. How does that, Taylor? Does that sort of give you a kind of an overview as to how programming languages are built on different programming languages, and the one below it is more detailed and more more tedious each level down? Yeah, you bet. An example in the real world might be you can drive a car without knowing how an engine works or how a transmission works. Because if you had to learn exactly how all the gears and whatnot in a transmission worked before you could drive a car, there'd be a lot fewer people driving cars out here. You don't need to know those details. You're trusting that the people at Honda or Ford or wherever know those details because you don't care about them. All you care about is, I want to drive my car and I want to get from point A to point B, hopefully in a little style. So you are abstracted from the concept of a synchro mesh transmission because you don't really care, unless you're into that thing, and you're into that thing because you either you love cars or it's part of your job or whatnot. Those people care about those things because they're supposed to and they love it. But when I'm driving my car to the store, I don't really care how a synchro mesh transmission works. I just care that my car works. Okay, sorry, I probably went a little deeper down that hole than I should have, but hopefully it's somewhat interesting information to some of you. Going back to Reborg, we know how to, or Reborg, going back to Python, we know how to add things to our lists now. So how do we remove things from our lists? And I said I had .del in there before. .remove is what I meant to have in there, but there is also a command called del, and I'll maybe show you both of them. So these are the commands that we're going to use to remove things from a list. So let's keep working with the lists we've got here. Let's say that I want to remove pi from this list. So I want to remove 3.14 from this list. When we're dealing with lists, all lists have an order of elements. And remember, we've been referring to that as the index. So when we had a string, we could refer to any of the characters by the number, right? So the H was represented by the 0 place, the 1, 2, 3, 4, because computers start counting at 0. So we could reference any letter by pointing at the index number. So if I wanted to access the O, I would say, well, that's at index 4. If I want to access the E, that's at index 1. You can do the same thing with lists, including the negative numbers. So using the exact same logic or the exact same idea that we did with strings, let's look at list 2 here. So if we look at list 2 here, the very beginning of the list is the string. This is list 2. So that would be the 0 element in list 2. The next thing in the list is the number or the integer 6. Well, that would be the 1 thing. The next thing in the list would be the 2 thing. And then the last thing in the list is the 3 thing, which is the Boolean operator false. And if you looked at the list above, there's more than that elements, or there's more elements in the above list, but list 2, those are the only 4 things in the list. What's in 0, what's in 1, what's in 2, what's in 3. And we can access things in that by using those numbers as well. So I'm just going to put a little comment sign there so that I can keep those up there while I show you how you can print out certain things. So let's print out from list 2, I don't want to print out all of list 2. I just want to print out something specific. Let's say I just want to print out the 88.8. So if I go to print, and this works exactly the same way as it did for strings. If I go to list 2 and I want to print out what's in the 2 slot, okay, I just need to put a square bracket and I need to put a 2 in the square bracket. And that doesn't refer to the number 2 or the string 2 or the float 2.0. That refers to whatever is in that place or that index in the list. In this case, that's 88.8. Comment this out for a sec. So when I print this list, or when I print list 2, the second index, it should print 88.8, and it does. If I wanted to print false, I would say, hey, print what's 3, print whatever's in box 3. You can think of it as, I don't know if you've ever seen a mailroom on TV where there's a whole bunch of square boxes built into a wall, and then somebody gets a piece of mail and you put it in their mailbox, and you put it in this mailbox, and you put it in that mailbox. It's just a way, and all of those are numbered. Here's mailbox number 0, here's mailbox number 1, number 2, number 3. I want to go get what's in mailbox number 2, so I access it by print this list 2. So if I want to print list 2, 3, it's going to print false because that's what's in that box. There you go, prints false down the bottom. It's all good. You can also print more than one thing. You can print from list 88. Oh, sorry, I should probably go from 1 to 3. Might make a little bit more sense. So when I ask it to print from 1 to 3, remember, just like in a list, it's going to start at whatever's in box 1, and it's going to print what's in box 1 and what's in box 2, and then it's going to stop as soon as it hits box 3. So what's in box 1? The integer 6, so it printed 6. What's in box 2? 88.8, so it printed that. And then it hit box 3 and it stopped, so it's not going to print out the false. And like strings, if you don't include anything after the colon, it'll start where you tell it to start, and it'll print to the end. And if you don't include anything in the first box, it'll print from the very beginning to wherever you tell it to stop. So if you understand string slicing, you understand list slicing. It works in exactly the same way, except instead of you working with the number of characters in a string, you're working with these boxes, which can contain all sorts of different data types. So that's why it's really, really handy, or really, really important, that we understand lists, because we can store a whole bunch of information in there, and we can access it really, really easily. Now, the lists that we're using in this class are all very short. They're going to have 10 items, 15 items maybe. So you could look through the list with your eyes and find the things you need to find, but you need to know that it scales up. So if you can find an item in a 15 item list, you can do it with a list with 1 million things in it. Okay, so the concept is exactly the same. The only thing that changes is the amount of data in the list and the time it takes the computer to process it and find it and check every item. For all the stuff we're doing in this class, the computer does it almost instantaneously. But in my Computer Science 30 class, one of the assignments is I give you, I think it's 100,000 pages of RNA code. So I don't know if you know your science, but ribonucleic acid. Okay, so those are all those little acids, amino acids in there. They all have a code, and there's 100,000 pages of this code for this bacterium. And what I ask you to do is I ask you to search through that list all of the amino acids, and also list how many times they appear. You could not do that, I don't even think, in your lifetime. There was over 1 million pieces of data. I could give you 100,000 pages, which probably take you all the way from the floor to the ceiling. And you have to go through that, and you have to write down all the specific amino acids, and you have to count them and keep a tally. And at the very end, you have to give me the results. It would take you an entire lifetime as a human being. But in Computer Science 30, the goal is to get you to build a program that does it. And usually the computer chews on it for a bit, but it doesn't do it instantaneously. I think somewhere in the neighborhood of 30 to 60 seconds it takes for our normal, admittedly kind of crappy school computers to churn through the data and go through the list and find all of the things it needs to find and add all the things it needs to add and then display it at the end. It actually takes a computer 30 to 60 seconds to do it, which in computer terms is a lifetime, because most of this stuff happens in a fraction of a second. Just think of Google, for instance. If you type something into a Google search bar and it takes more than 0.5 seconds for your results to pop up, you'd be kind of ticked, right? We're very used to computers doing things very, very quickly. Okay, so if you typed in a search term and it took Google 30 seconds to give you results, okay, you'd be upset about that because you're just used to computers doing things really fast. And the amount of data that Google has to go through, the programs, you know, running Google and their servers and all the data they've got stored, the amount of money, the amount of programming excellence, and the amount of ingenuity that has gone into you being able to get those results in a fraction of a second is absolutely staggering. You should read about it if you're interested in this stuff. It's really incredible, the level of technical proficiency that these really creative and genius, frankly, people behind the scenes at the big companies are putting into their material. It's unbelievable. Okay, so we know how to add things to a list. We know how to access things from a list. We know how to slice lists using very similar techniques that we used with strings. But I said let's start removing things from lists. So now we've done a quick review on what index means and how index refers to basically the number of the box that you're accessing. Now we can get to the part where we're actually, you know, able to delete some stuff. So let's look at .remove first. So if we do a let's look at list one, or list one dot remove. Okay. Now we need to put a value in here of the thing that we want to remove. So what is it in this list that I want to remove in list one? Let's say I want to remove 4. Okay. So if I want to remove 4, okay, it didn't show me that anything happened, but that's because I didn't tell it to print after. I just said, okay, remove the 4, and you know, now after the fact, I should probably print it, and let's check if it actually did what we wanted it to do. So let's print list 1 after that. Okay. Oops, 4 is still in there. Okay. Did I make a mistake? Get rid of hello. Yep. I'm not sure why the 4 did go away, unless I had 2 4s in there. But in any case, I deleted the line that said 4. That's why. Okay, that makes a lot more sense now. Okay, so in this case, I put in .remove, and instead of appending, where I put in the piece of data I wanted to add to the end, when I put in .remove, and then I put in the thing I want to remove inside the brackets, it looks through the list, it finds it, and it removes it. So that when I print it after I remove hello, you'll notice the first version had hello in it, and the second version, it's gone. Okay, so I can't see hello anymore. So it's gone forever at that point. You know, you can remove whatever you want, right? So list 1 remove. What should we remove? 88.8. X not in list. List. String integer 0, 1, 2, 3, 4, 6. Remove X not in list. Huh, maybe that only works for strings. Yeah, you learn something every day. I'm pretty sure that worked with all data types, but anyway, that's how you can delete stuff with a with the remove command. But we have to find a way to. Oh, it's .pop. That's what it is. So anyway, .remove you can use with strings. This is probably the one that's going to be of more importance here. If you .pop, P-O-P, it basically means you pop it out of the list. So P, and then student job range. Let's .pop 2. Print out. Okay, so this is the one that's probably of more value to you than .remove, because as I just demonstrated and had forgotten apparently, .remove doesn't appear to work for other data types. It worked fine for string, but it didn't work for other data types. So when we are wanting to get rid of any item in general using an index number, this is going to be much more sort of user friendly. So if we look at list 1 and we look at the index numbers of these things. So the 4 would be in index 0, 5.5 is in the 1 position, 3.14 is in the 2 position, hello was in the 3 position. I went pop 2. So what that does is it looks for the 2. So that's, and when I say 2, I mean the index 2, the position 2. So that's 0, that's 1, that's 2. So we would expect that it would remove the value 3.14. So basically, if you ask me, hey, I see pi in that list, the number pi in that list, get rid of pi, I would say, okay, it's 0, 1, 2. So I'm going to pop 2 out of there, and then we're happy. Or maybe you'll say, I don't like the fact that it says pi at the end of that list. I'll say, okay, well, I will pop that out as well. So list 1 dot pop, and what does high represent? Well, let's think. It's 0, 1, 2, 3, 4, 5, 6, 7. High is the 7th thing. So I want to pop out the 7th thing. And this is going to cause a problem, and I want to demonstrate why. So I'm going to pop out the pi number, 3.14, and then I'm going to print the list. So I'm going to print list 1. Then I'm going to try to pop out the 7 item, which is high. And I think this is going to cause a problem. And I'll explain why in a second. So let's run it. And what happens? Okay, so it popped out the 3.14, no problem. I also had a remove in there from before that I'll just get rid of that for now. So what did it do? It popped out the 3.14 and then it printed it. So that's great. So there was the original. And did I ever print the original? I didn't even print the original. I'll print it up here. Print list 1. Running into too many print statements here. Okay, so print list 1. Okay, so this is the original list. Oh, good grief, Dunbar. Getting most crazy. This is the original list 1. Okay, and then we appended these 2 things to list 1 and printed it out again. Okay, and then I told it to get rid of the 3.14 by popping what was in list or position 2. Okay, so I popped out what was in position 2, and what was in position 2 was the 3.14. So that's great. Then I printed the list. Then I popped out what was in 7, and then I printed the list again. For some reason, I printed it twice. Now, what you'll notice is, okay, the 3.14 is gone here, but what else got deleted along the way? Okay, the 99 got deleted. That's because I forgot that up here, I took my original list and I added 99 and I added the end. So I actually had more things in the list than I thought I did because I had added those items and forgot that I did it. So I'm just going to turn those off. So when I run this again, okay, now we've got that problem that I anticipated happening. And here's why we had that problem. If we look at the original list contains, and I'm going to get rid of list 2 now because it's just probably getting in the way. So I'm just going to refer to the index numbers here. So index, that's what's in the 0 position, that's in the 1 position, this is in the 2 position, 3 position, 4 position, 5 position, 6 position, and high is in the 7th position. So the 7th memory box basically of the list. So if we look past all the gray code and we look at pop 2, it's easy to pop 2 out there. We just look at what's in the 2 slot, 3.14, that's great, it pops. And then theoretically, or you think that maybe I should be able to pop out what's in number 7, which is high. Now, here's why it caused the error. As soon as you pop out list 2, okay, as soon as you pop out the 3.14, the numbers of everything else shifts to reflect that. So as soon as you get rid of 3.14 in the 2 position, it means that hello shifts back, and hello is now number 2. And then true shifts back, and true is number 3. 4 shifts back to 4. And then everything shifts back a space to accommodate that. So it did, the first step it did is it got rid of the 3.14 in the 2 slot and slid everything else back, which means by the time I got down to this line of code, when I tried to pop high out, high was no longer in position 7. There's nothing in position 7 because our list would only go up to index 6 now. So if I wanted to pop high out, I would have to pop 6 instead because I have to remember that when I delete something from a list, the rest of the list shifts back to reflect that. So if I change it to 6, now it works fine, right? The first thing it does is it pops out the 3.14, and then the second thing it does is it goes and pops out the high. But if I didn't remember that, I might keep getting this error. And this is an error you're going to see a lot if you do looping, and you're going to see a lot if you use lists, and that is index out of range. And what index out of range means is that you tried to tell the computer to access a memory slot or one of the memory boxes that isn't there anymore. So if I try to access list 1, if I try to access 8 or 9 or 10 or 100 or 1,000, it's going to give me this error because they do not exist. These only exist up to 7 in this case. And then after I get rid of one, it only exists up to 6. And then I get rid of another one. Now everything's been shifted back, so it only exists up to 5. So if I try to access, let's say I try to print out whatever is in slot 6 now, it's no longer there. So if I try to print list 1, and then the 6th element in list 1, well, at the very beginning of our program, the number 6.665 was in the 6th slot. However, after we popped out this element, okay, then high was in the 6th spot. But then after I popped out high, everything shifts back. There is no 6th spot. So that's why it's going to give me an error again, because I've popped out 2 items, which means everything shifted over, and it shifted over to the point that 6 no longer exists. Okay, so it's important to understand that when you pop things out of a list, it changes the list for good. Now, if you want to access the last item in a list, instead of trying to count forward, it might make more sense to do it from the back. Now, you can do this with strings. I'm pretty sure you can do it with lists too. Yeah. I've just got to print the list again. So remember how I said I'm going to get rid of the high at the end, and then I counted. I said, I don't like the idea that high's at the end of this list. I want to delete it, or I want to pop it out. So I went and I counted. I went, that's 0, 1, 2, 3, 4, 5, 6, 7. It would have been easier for me to just pop out -1, because I know whatever -1 is, it's at the end of the list. So if I pop out -1, now it pops that high out at the end of the list. Well, if I pop out -2, it's going to pop out the second thing. So I'll get rid of this line. So I'll start with my original list, and I say pop -2. So what it's going to do is instead of starting at the beginning of the list, it's going to go to the end. And it's going to say, okay, high is in the -1 position, and then this is in the -2 position. So this first line here is index. Basically, I'm just going to put FF, and what that's going to stand for is from front. Okay, and this would be like index from FB, from back. So if we go from back to front on this, that would be -1, -2, -3, -4, -5, -6, -7, -8. So this would be -8, and -7, then -6. This would be -5. This would be -4, -3, -2, and then the very last thing is -1. Maybe space these out a little bit better. So 0 represents the 4, -1 or -8 represents the 4. 1 represents the 5.5, and also -7 represents that. So there's really 2 different ways of getting at each piece of data inside your list, just like with strings. You can either start at the front and count forward, or you can start at the back and count toward the front. So if I'm popping -2, it's really the exact same thing as me popping out 6. So I would expect that if I pop out -2, that 6.665 is going to come out of my list. So let's see what happens when we print it. Okay, so this was the original list. And as you can see, after I popped out -2 and printed it again, the 6.65 is gone. Okay, so if I want to pop out 3.14 again, instead of popping out 2, I could also pop out -6. It stands for the exact same spot, just counting from the back instead of from the front. So now you notice the original list has 3.14. The new list doesn't have 3.14. So that's how you can remove things from, remove any data type from a list. And it's probably a better way than using remove. I use more than remove, but remove is another way to do that. Okay, so now we know how to create a list. We know how to add to lists. We know how to concatenate lists. We know how to remove things from lists. Now let's get to some stuff that we can that we can use to really save ourselves some time in building certain types of lists. So I'm just going to comment all this out, and we're going to move down to sort of the next item. We did all the slicing. Strings to list I might actually leave for a different day. Let's go here because I think this is really important, and it can help you build things really quickly depending on what problem you have to solve. So it just says use loops to populate lists. Well, let's just say that I wanted to create a list of all of the numbers starting at 0 and then going to 1,000, but I only wanted to do even numbers. Okay. It would take me a long time to go, to make my list and say, okay, even nums equals, and then list. Okay, 0, 2, 4, 6, 8, up to 1,000. Take me a long time, right? So instead of doing that, what you can do is you can use a loop to populate the list because the computer can do it really quickly. So because I know how many times I want it to do it, okay, I can make a loop using a for loop. Because remember, when you know how many times you want to repeat, use a for loop. When you don't know how many times you need to repeat or how many times to loop, that's when you got to use a while. So this time I know how many times I need to loop. So I'm going to go for x in range, okay, 0, and I'll say 1,001, and then I'll also say 2, because remember the last one is how many you want to step by. So it's going to start at 0, and then it's going to skip over 1, and it's going to go to 2, and then it's going to skip over 3 and go to 4. So if I do for x in range, and x is just a variable, I could call it for num if it makes it easier to read. For num in range, starting at 0, ending at 1,001, skipping by 2 every time. Let's add that to our list, and we add things to our list by using append. So it would be even nums dot append, and what are we appending? Num, because remember num is just the variable inside this for loop that changes every time. So num is going to be 0 for the first loop. It's going to be 2 for the second loop. It's going to be 4 for the third loop. So really, that's what I want to end, or that's what I want to add to my list. So for this 2-line structure right here, I just created 1,000. I just created a list with 500 pieces of data in it. Took me no time. It'll take the computer no time. And if we print the result of that, so this was what was called even numbers. If I print the result, it'll take no time. So watch here. Boom. There's a list of every even number between 0, okay, starting at 0 and ending at 1,000. It took this much code. And you can imagine how long it would have taken me to type all that in. And you know what? It doesn't take a whole lot more time to go to 10,000. So let's try 10,000. Boom, done. It's an even bigger list. Look at how big this list is. We're talking like matrix code now. Should we try 100,000? Okay, now we're going to get to the point sooner or later where my computer just can't handle it. But let's try 10,000 or 100,000. It didn't take very long to do 100,000. That was pretty quick. But I mean, we're already talking about like hundreds of pages of code that I'm scrolling through that took a computer a fraction of a second. You want to print every third number? There you go. Just change that to 3. Do it again. Boom. Now you got every number starting at 0, going up by 3 from 0 to 100,000. So you can use these loops to continually add things to your lists and basically generate these huge lists, at least when you're dealing with numbers, really, really easily. And Computer Science 30, we extend this, and if you remember that little DNA or RNA project I was talking about, you can make it so that you take this huge text file, just a big digital file, like a Word document full of DNA codes and amino acids. You bring it over to Python, store it all in a list, go through the list and do whatever you want to do, and then you spit it back out to a Word document saying, hey, you gave me 100,000 pages worth of data. I gave you 1 page back that said there are these 26 elements, and these are the numbers for each of them. So you see how we pull data from one source, do a whole bunch of stuff with it, and then get what we need to get from it, and then spit it back out to a different format, because the person who asked for that data doesn't care about Python or doesn't care about programming. That's why they asked you to do it. That's why it's your job. They said, hey, I'm going to give you a big Word file with, here's 100,000 pages of Word files or a Word document. I don't have time in my life to read this and find out how many of this particular strand of DNA there are. Okay, create a program to do that, and all I want back from you is 1 page on a PDF or on a Microsoft Word document that has the number on it. That's all I want from you. I'm going to give you 100,000 pages. You're going to give me one page back with the number that I need. They don't need to care how you do it. Okay, so you take big pieces of information, you store it appropriately, you work with it, and you give them back the exact piece of information that they need. And that essentially is how things work. I mean, that's why computer programmers they're in demand. They will continue to be in demand, in more demand the more things that are automated, and they are paid typically very well, at least in first world countries, because there's a very specific set of knowledge and skill that you need to be able to do those sort of things, and very few people have them. In fact, I think probably you will have heard from your parents or your grandparents, or people in your life who are elders, oh, I'm no good with technology, right? Things that you think are simple, like every time my dad needs to do something on the computer, invariably I will get a telephone call saying, I'm no good with computers. How do I do this? And I'll be like, okay, Dad, you do this, you do this, you do that. There are very few people who have these really, really specific sets of skills that can take these large sets of data and do special things with them and get the answer. And that's why it tends to be in demand. It tends to be like very well paid and respected positions. Okay, so that's how you could use an example of how you could use a loop to populate a huge list. But you could also use a while loop to do the same thing. Let's say that you want to ask a person for a bunch of test scores, and they tell you when they want to quit. Well, this is the kind of loop. Okay, so maybe instead of even numbers, I'll call this test scores. Okay, now this is the kind of loop where I don't know how many times it's going to loop, because the user could put in one piece of information, or they could put in 100 pieces of information. I don't know. Okay, so I'm going to use a while loop, and I'm going to use a flag to tell me when to stop. So I'm going to say the flag is going to be -1. Okay, so I'll start my flag at 0. So when I build my while code, and we've done this in Reborg, and we've done this in the first several assignments, while the flag is equal to 0, okay, which it is at the start, so I know it's going to run once. What do I want to happen? I want an input statement. So I'm going to say score equals I want it to be an integer. So let's say the score is an integer, and I want input from the user, and basically it's going to be enter grade, okay, and then -1 to end, or while flag equals 0. I'll say -1 to end, because that's kind of a common thing. So while flag is equal to 0, it will continue to run. While flag is not equal to 0, it will continue to, while flag 0, it's going to run. When flag hits -1, it's going to stop. So what I'm going to do right away after this is I'm going to put in a break statement. So if score, the only time we have to end this loop is if they type in -1, right? So if score is equal to -1, let's break. Okay? And break was just a handy way to get out of a loop, right? So if you ever see break inside a loop, it means if it hits that line, it skips outside of the while loop and it goes down to the next one. Okay, so I changed my my list name, so now it's test scores. Okay. So what this should do is this should allow people to type in as many scores as they want, and when they hit -1, they're done. So what I want to do is, as long as that score isn't -1, I want to add it to my list. So we just used an append. It's the exact same as it was before. The loop is different, but the logic for adding, or the ability to add things to a list, hasn't changed. It's just test score.append, except this time I'm going to append whatever score is. And so I'm going to end every score. So if you look at the order in which this occurs, I created an empty list to store all the test scores. I created a flag that I just set to 0 for now. And frankly, I didn't even need a flag for this one. I could have also just said while true. Okay, so if I want to make this even easier, I'll just kind of build my flag into this part right here. So while true means it's going to start and it's going to keep going until I somehow tell it to stop. Okay, so while true, score is going to equal what they type in. So if they type in -1, okay, if score is equal to -1, I'm going to jump out of my loop. If they put in anything except -1, I'm going to try and make it an integer, and then I'm going to store it in test score. So I'm taking my empty list and adding something to it. And they can do that as many times as they want. And when they finally hit -1, I'm going to print all the results. So let's just give this a run, and we'll see how it works. Okay, so enter a grade 100, enter a grade 25, enter a grade 68, enter a grade 15, enter a grade, -1, done. So they entered in this case, 4 grades. They entered 100, 25, 68, and 15, and then they told me I'm done by typing in -1. And when I printed off my list, notice that those 4 grades are in the list. Now, -1 is not in the list because I have the break, I have the logic that tells me whether they're done or not before I add score to the list. If I had these backwards, then it would still break out of the loop, but what it would do is it would actually add -1 to my list of scores, which I didn't want to do. I knew that anytime I see a negative number, or a -1 in this case, that's not a real score. That's them telling me they're done entering. So that time I entered 4 scores, but the beauty of the while loop is I could enter 1 score. So let's say I just enter in 100, okay, and I can hit -1, and my list can only be 1 long. Or let's say I want to enter in, more than 1 or more than 4. I can do, there's my score, 34, 54, 76, whatever I'm typing in, doesn't matter, as many as I want. When I hit -1, program's over, and I can spit out that list that I built using append. So now how to append, how to build lists and make them bigger using a for loop and kind of automating it. You also know how to get user input and use while loops so that you can put any number of pieces of data in there. Okay, it depends on what does the person need to enter. So you can use while loops while populating lists as well. So that's really handy. Okay, we're getting up on hour 25 right now. I did have 4 more things that I wanted to go through with lists, but these things are for assignment 13 largely. I might, because assignment 13 is due on the 20th. So I think what I'm going to do is I'm going to move our maybe move our Wednesday meeting to Monday morning. That way we can go through these last sort of 4 or 5 list items on my list items, 4 or 5 concepts related to lists. And if you were struggling with any of the programs on number 13, you'll have that little extra session to help you with the lists and the looping and how you use dictionaries and things like that to get you through assignment number 13. So look for our Wednesday session to be moved to Monday morning. Monday morning? No, Monday afternoon. My mistake. It was supposed to be at 1:30 on Wednesday, so it'll be at 1:30 on Monday. I'll put an announcement. I'll send an email, and then we'll go through those last 5 or 6 things that I think you need to review with regard to 4.6 and 4.7. Which just leaves us with 4.8. Now, 4.8 we don't do a whole lot of work with. I want you to understand the basics of data validation and of sort of data sanitization. It doesn't make up a big part of this course, but you really need to know 4.6 and 4.7 quite well. Okay, so we'll call it a day there. I'll post this recording as I normally do, and we'll meet up again on Monday and do a few more details. So. Please continue to work on your assignments. Please continue to email me when you have questions. And please, if you run into things that maybe there's 3 or 4 problems you run into when you're building your programs, just make a little list of them and then bring them to the live session, because I love trying to help people solve problems in real time. And also remember, if you have a question or if something's not making sense to you, there's probably at least 10 other people that are having the same question and might not want to kind of raise their hand. So never be afraid to bring certain problems, questions, request confusion areas to these live sessions as well, so that we can help everybody. I'm going to stop recording now, and I'm just going to ask, does anyone have any other questions specifically that I can help them with before we call it a day?
Will the next Python exam also be 2-parted?
It will be 2-parted. The practical portion is weighted for less in the second exam, mostly because there's more questions on the theory part where you actually have to type some code in. So the first exam is probably like 60% theory, 40%, somewhere in that neighborhood, practical. For the next exam, I'm pretty sure it's something like 75% theory, 25% practical, as far as how the grades work out. That answer your question okay?
Yeah, thank you.
Yeah, no worries. Zane's got a question there. I'm having trouble with the name validation assignment. Okay, what particular part of that, Zane? haven't been able to get the while loop working properly. Okay. So tell me what I should type in. Am I still sharing my screen? No, I'm probably not sharing my screen. Hold on. I'll share my screen again. Okay, tell me what to type in. Okay, when a user types in something like a string or whatever, well, it's defaulted to a string, right? So if you have input, type something in, it's going to be a string. It keeps saying not a name. Okay, so how did you test if it was a name or not? What did you use to try to test if it's a name? Okay, but you got to give me one of them, or more than one, because chances are the solution to your problem is really simple. But I have to know what you tried. Tried is numeric. Okay, well, if you don't do anything and you use is numeric, remember that X is a string right now, so it's going to check that string to see if there is anything that's numeric in it. So if X dot is numeric, then let's have it print there is a number. Else, print no number. And let's try some data, okay? So it's going to say type something in, and I'm going to type in Brennan. And it told me no number, which is correct. Let's try typing in 55. There is a number, which is correct. Let's try something else. Type in Brennan 55. No number. Okay, now we've got a problem there, right? So that solved a couple of things. It worked if it was just a number, and it worked if it was just a string, just a name. It did not work when I had both a string with characters and a number. So what else could you try? And using more than one of these is fine. So you've already, just by doing this much, you've given yourself some information. You said works for just numbers, works for just names, fails on names with numbers. So you've already solved 2 of your 3 problems. Okay, so you've got is alpha and is digit, okay, using a combination of those 2. Okay, so now let's just see what happens if we use is alpha. In this case, it will be, we'll print alphabet only, or we'll print not just alpha. Okay, so let's try some data. All right, 55. Not just alphabet, which is true. Brennan. Alphabet only. Great. Brennan, 55. Not just alphabet. Great. So that passed all 3, didn't it? Okay, are there any other potential problems? It's a great start. Are there any other potential problems you can think of? No, let's try the floats. Passes. Passes. Ooh, that's an interesting one. Fails. I actually didn't ask you to worry about Boolean. How could we check for Boolean though? Be pretty easy to check for Boolean, right? Because what we could do down here, is in the else, because if it is alphabet only, or sorry, in the if statement, we could also check before we print that out. We could check is, and then put the actual string true in x, or sorry, if true in x, not is, if true in x, and we can print as bool, and then do our else, print alphabet only. If true is not the only Boolean, right? If true in x, or true or false in x. How about that? Okay, now I can type Brennan true. And it says has bool, right? So you could check with bool very easily just by adding in one more if statement. There's one more possible problem though with is alpha. And I haven't been checking with it. I've decided to go easy on people when I'm marking this, but there's one more potential problem. And here it is, okay? I think we could agree that that is my name and that that is probably an acceptable name. It says not just alphabet. Do you know why it says not just alphabet? There's a space in it. So sadly, this recognizes a space and says a space is not an alphabet character. And it's right, it's not an alphabet character, but we wouldn't want to reject, okay? We wouldn't want to reject Brennan space Dunbar as a name because it clearly is a name. Okay. Now, I'm not asking you to go so far. There have been students that have solved this problem, that have used logic and some other additional pieces of code to solve this problem and do it effectively, and that's great. I'll show you a way around it. Okay, this isn't something that I specifically taught, but sorry, where was I here? If is alpha, print is a name or is alphabetic. You could put in an extra check down here in the else statement to figure out if it's got a space in it or not, okay? So if it's got a space in it, it might still be okay. Okay, so before I check if it's alphabetic, I might want to check and see if there's a space in it and or replace that space. So one way you might do this is create a temporary variable. So maybe I'll just call it temp name equals. And what I want to do is I want to replace any spaces before I check. So what I would do is I would take my x and then I would do dot replace. And then what I would replace is a space. And then after the comma is what you replace it with. I would replace it with nothing. So what this is doing is I'm creating a new variable, just a temporary one, just so I can check the spaces. So it looks in the string x and it says replace, okay, whatever's in front. So the first thing I have is quotes with space in it. So that would be the white space, right? So if you see a space, what I want you to replace it with is no space. So that means when I print out temp name, it should print out whatever you type in without spaces. So let me just show you that. Print temp name. Okay. So if I type in Brennan space Dunbar, you see how it prints out Brennan Dunbar without a space? And then what you could do is you could check if all of these are characters. So instead of checking X is alpha, you could check temp, what I call temp name. And now we'd be relatively certain. And even if you're using temp name to check, just take the space out and check if the rest are all letters, you could still print out the original, right? So I could still print out X, comma, is alphabetic, okay? Or X, comma, not just alphabet. So now this will pass this test as well. Okay, so type something in, Brennan space Dunbar space name. So I've got 2 spaces in there now. But when I check, I print out my temp string just so I can see what, this is just kind of me debugging on the fly. So I can see, did it actually strip out all the spaces? Okay, great, it did. And then when it checked this particular string using is alpha, it said, okay, everything that's left in there appears to be a letter. So that's why it's saying it's alphabetic. And then instead of printing the temp string, I just printed the original, right? And this should still work if I put in spaces. Let's say Brennan space Dunbar space 5. Now we would want this, or space 5 space dot 555. We would want this one to reject, right? So it rips out the spaces, but after it rips out the spaces, it still runs the is alpha check, and it says, hey, I caught a number in there, so it's not just alphabet. So that's one way that you could get rid of the spacing problem. Again, I didn't mark it with spaces. I said if you could figure out that it's just alphabetic letters, or if you could use any combination of is alpha, is numeric, is alnum, anything. There's lots of them, and there's lots of combinations you could use. If you made it work so that I put in an integer, a float, a name with an integer, a name with a float, and it spit all those out, and it accepted a name, that was good enough for me. But like I said, some students kind of tried to go above and beyond and take care of things like spaces, which is good, okay? Because they had to go out and do a little research on their own and test it and make sure it worked and send it in. Like, that's great stuff. Okay, any other questions? I probably shouldn't have given you that much information. That was too much information. Probably should have made you guys work a little harder for that one. Not seeing or hearing any other questions, so probably time to call it a day and a week. Thanks again for coming. Again, I'm always available. If you have any questions or struggling with anything, just send me an email. I'll try to point you in the right direction. And have yourself a wonderful weekend.
Have a good weekend.
Yep, you too, Romilly. See you on Monday or somewhere thereabouts.
See you.
No worries, Zane. Catch you later.